and both are related to limit orders. Yes, so
first, thank everyone for coming, and let me also extend warmly welcome to our guests from Imperial College London. So today I'm going to talk about scoring limit orders and its application in algo-trading. This is based on a joint work with my PhD student, Chen. So if you have any comments and suggestions, so please let me know. Okay, so before I get into the details, let me first give you an overview of what we do in this particular work. So we developed a stochastic dynamical model to analyze the performance measure for limit orders at better quotes for a class of liquid assets, and I call this performance measure as the order score, similar as like a credit score. And then we estimate and using the model using Nasdaq's order book data, and we validate the model using backtesting simulations. And finally, we apply our model in guiding order cancellation decisions using a multi-undervalue learning approach, and we illustrate the empirical performance of several popular value algorithms. Okay, so here the agenda of the rest of the talk. I'm going to give you a quick overview of the background and motivation, and then I will be talking about data, models, and decisions. Okay, so let me start with the background. So most financial markets nowadays are electronic, and the key ingredient in many modern electronic trading algorithms is the effective use of limit orders. So the main objective of using limit orders is to capture a portion of the bid-ask spread while you try to minimize the risks, including the non-execution risk as well as the adverse selection risk. So adverse selection risk generally arise when you trade with someone who has more information than you or who is just faster than you. But at a mechanical level, if you're a liquidity provider, you have placed a limit order in your order book, and your order might be just one of the last in the queue to be filled. And after your order is filled, the market then trades down to a low bid, and this creates immediate loss for you. So the motivating question for this work is that how can you avoid such kind of losses or to mitigate such type of risk? And if you are a liquidity provider, okay, when should you cancel an order that you are not interested to get it filled? Okay. All right. So we are going to sort of address this type of problem for a class of liquid assets called elastic assets, which has received lots of academic attention in the academic literature. So these type of assets typically have bid-ask spread being 1 tick, so that's sort of 1 cent, usually for stocks. And if the assets is traded at a low price, this means that the tick size relative to the asset price is higher. So the revenue margin for providing liquidity on this type of assets is higher. And one can imagine that market makers or liquidity providers can be active doing liquidity provision of this class of assets, which has also been observed empirically. And in addition, you can also observe that there will be long queues of limit orders sitting in the order book waiting to be filled. And in general, liquidity providers try to compete for front queue positions in order to obtain execution priority of their limit orders and reduce the adverse selection risk. Okay, so let me quickly go over order book and discuss two macrostructure features that will be important in our work. So this is a snapshot of Starlight order book where I've only displayed the top 3 levels. So for us, what is important is the top 1, okay, the top of the book, which is the best bid and best ask. So best bid corresponds to the price, the highest bid price in the order book. And the last column basically corresponds to how many shares of limit orders sitting at that particular price level. Okay. So imagine now you are a liquidity provider. You have an order that it has, waiting at the best bid. Okay. So regardless of what type of performance measure we want to look at, one thing is important is the relative queue position of your order. Okay. So this basically measures, how many orders are in front of you compared with the total size of the queue at the best bid. Okay. And another macrostructure feature that has the, that is more subtle but has received, but that's also important, is called the bid-ask-Q imbalance. So there are sort of different equivalent definitions of this quantity, okay? But this basically measures sort of the different size on the best bid and the best ask, okay? So I have used this particular definition so that the imbalance basically lies in the interval from 0 to 1. Okay, so why this quantity is important? There have been lots of empirical evidence showing that this feature significantly impacts the order flow and the field probability of orders. And in fact, many practitioners use this type of signal to predict when the price will move for the next tick. All right, so now let me define sort of the measure that we want to look at. So throughout the talk, okay, I'm going to focus on a limit order that is placed at the best bid, but you can also think of an order that placed at the best ask. Okay, but we are only going to focus on these top two levels. Okay, so the performance measure of such a best bid order is measured as follows. This is the execution price of your order, or just the limited price of your bid order. Okay, and this is sort of the fundamental value or the fair value of the asset after your order is billed. Okay, so what we are doing is we are measuring the difference between the execution price of this limit order compared with the fair value after the order is executed. Okay, so in other words, if you buy this asset at $8 and after your order is filled, the price moves down to, let's say, $7, then you lose $1. Okay, if your order is filled and then the fair value is still at $9, then you gain $1. Okay. All right. So I will call this performance measure as order score, where this there are two random times. T field corresponds to when the order is filled or executed, and the T cancel corresponds to when the order will be canceled. For example, you might want to cancel your order if the best ask moves up. Okay. So this is of course. This quantity depends on what kind of information you have. Okay, so you can use lots of information. For example, including the relative position of the order as well as bid-ask imbalance. Okay, so of course, to talk about this performance measure, we first need to talk about how we can measure the fair value of the asset. So we are not going to use the usual bid price, which is the arithmetic average between the best bid and the best ask. Instead, we are going to use this Macroprice, which is just the depth-weighted bid price. Okay, so this quantity has been used typically, or its variant has been used by financial practitioners as an estimate for the fundamental value or the fair value of the asset. So what is Macroprice? This is just a convex combination of the best bid and the best ask prices with weights put on the best bid and the best ask sizes. Okay, so here is a simple example. This is the best bid and the best ask with the corresponding ask sizes. And what is the Macroprice? You just do this convex combination. In particular, you see that this term is just the bid-ask imbalance. Okay, so the Macroprice captures the bid-ask imbalance. Now, of course, if suddenly a surge of market order flows coming or a large market order comes, so that it depletes the whole cube over here, then the new best bid price, let's imagine it becomes 1 tick below. Okay, and the new bid size becomes 800. Then the Macroprice, according to this definition, okay, will be becoming this number, which is slightly lower than the previous best bid. All right, so before I talk about the data and market simulator, let me quickly go over related literature. So in the market macrostructure literature, there have been statistical models, okay, and we discuss how the expected profit of limit orders depends on the Q position as well as the fundamental value of the asset. And these models are typically used to derive competitive equilibriums, okay, or competitive spread, where a market maker or liquidity provider earns zero expected profit on average. And a dynamical model for valuing a limit order based on its Q position only showed up very recently by this work. And in this work, their model is essentially one-sided in the sense that the field probability of orders is independent of the bid-ask imbalance. And as I mentioned earlier, lots of empirical studies have shown that this is not the case. Okay, the field probability of orders will depend on this signal bid-ask imbalance. So our model will try to take into account this bid-ask imbalance into the model. Okay, so let me talk about the market simulator and the data. So the aim of doing this is twofold. Okay, the first is that we have this performance measure, which is sort of defined mathematically by a conditional expectation. But now we want to first look at how it behaves on the market in the sense that whether we can do some kind of sample average approximation for that expectation. And second, we build this market simulator so that we can validate our model later on. Okay, so the data we use is Nasdaq's massive data. Okay, so here is a table for a sample of 5 rows of massive data for the stock Intel. So we do not need to fully understand what's going on in this data for those of you who are not familiar with this. But the bottom line is that this is massive data, meaning that it records every order book event that occurs in the market. Okay, and with this type of data, what one can do is you can construct a market simulator. So what that means is that we can simulate the dynamics of artificial orders. Okay, so what one can do is we can randomly insert artificial orders at best bid price level in the order book with different relative Q positions and imbalances. Okay, and then you can just follow the matching rule of the exchange and then update the status of your order at every event time. Okay, so of course in constructing such kind of market simulators, of course we need some assumptions. First of all, we need to assume that those artificial orders are of infinitesimal or very small size so that they won't impact the market. Okay? And second, particular to our problem for simplicity, I'm going to assume that if the best ask price moves up, then the best bid order that I placed, okay, will be cancelled. Okay, then once we have this market simulator, you can compute what is sort of the realized score of an artificial buying order. So according to our definition, if the order is filled if the order is cancelled before it's filled, then the order score will be 0. Okay. Otherwise, if the order is filled before it's cancelled, then according to our previous definition, the order score or the realized score of such a buy limit order will be the Macroprice post-trade minus the bid price.
Can I just ask a
Sure.
question? So what is the priority rule that you use?
Okay, this is first in, first out, the time priority.
So if you pose to artificial order, can you go in front of the queue or?
The best you can do is you just you insert the order at the front of the queue.
But how is that possible? I mean, you were talking about these tick sizes before, and if the previous orders are already at the bid
So of course, the most straightforward way you just append an order at the end of the queue, right? You can do it at the end of the queue. But as I mentioned, we are looking at this performance of limit order conditioned on some microstructure features. So now imagine, just forget about these artificial orders. Now just imagine you have an order at the front of the queue. Okay, we want to measure its performance. And this is what artificial order is doing. So you need to condition it on some sort of microstructure features. All right, so this is a very typical picture of order score. Essentially, as I mentioned, we are trying to do some kind of sample average to approximate the expectation or the expected profit of limit order that we have defined. Okay, so let me explain. On the vertical axis, we have order score, and on the horizontal axis, we have the bid-ask Q imbalance. So I have cut the bid-ask Q imbalance into 50 groups, 50 pins, where on this side it means that the bid size is much smaller than the ask size, so that the price might move down. Okay. On the other hand, if you have bid-ask Q imbalance close to the 50th group, meaning that ask size is much smaller compared with the bid size, so the price might move up very quickly. And in that case, according to our assumption, the order it will be cancelled. This is why you observe that at the right-hand point, most of the order score is very close to 0. Okay, and another thing that you can observe from this picture is that if the bid-ask Q imbalance is close to this side, meaning that the bid size is much smaller than the ask size, you can see that order score can be negative. Okay, so this means that orders, especially those at the back of the queue, might get filled only when their limit price was exceeded. Okay, what that means is that after your order is filled, the macro price goes down. Okay. Now in this picture, of course, we have many different curves. So this top one corresponds to you insert the order at the front of queue, meaning that the relative queue position of the order is basically like top 1%. Okay, and you also have the bottom one corresponds to you insert your order at the end of the queue. Okay, so of course in general you can observe that the queue priority matters. Okay, so the better your queue position, okay, you are in the front line, then the order score will be larger. Okay, of course, as I mentioned, okay, what we are doing is that we are sort of computing the order score conditioned on these two macrostructure features. All right, so next I'm going to talk about a model. Okay, but before I talk about model, it's a parametric model. Okay, but before I talk about that, I really need to see, first address a particular issue. If we already have such a picture, okay, which is model-free, which is non-parametric, why we need a parametric model? Now the reason for that is, in order to obtain these kind of pictures, okay, you need to have data across a relatively large time scale. In this case, it's like 60 trading days, 64 trading days. Okay, so if you only work with like 1 day data, 2 day data, you are going to get very, very noisy estimates. Okay, so this is like you do not have enough sample size in order to estimate the mean. Okay, all right. So if you have a parametric model, then you can capture possible daily or even intraday variations, while this non-parametric model-free approach cannot capture that. All right, so this is why I'm going to propose a parametric model to study the order score. Okay, so recall this is the definition, and without the loss generality, I'm assuming the best bid being 0. Okay, this basically, this is not a key issue. All right, so once we do that, okay, this quantity is 0. All right, so here is a quick overview of the key model elements. Okay, we have 2. The first one is that for the fair value of the asset, we need a model. Okay, so in this case, I'm going to use a discrete time Markov chain. Okay, it's simple, but actually we start with simpler models like random walk. Unfortunately, it does not work very well. Okay, so we move on to Markov chain. And second, we need a model for the time to fill. Okay, and in this case, I'm going to use a normal hidden boundary model for the middle order executions. Okay, so now let me sort of discuss the details of our model. First of all, we will model the Macroprice as a Markov chain, okay, on a finite state space with transition probability matrix P. This Markov chain has 2 absorbing states corresponding to price changes. The first absorbing state occurs when the best ask price moves up, and in this case, by assumption, our best bid limit order will be cancelled, as this essentially determines what is the time to cancel. The second absorbing state corresponds to when the best bid moves down, and in this case, the buy order can be adequately filled with this particular order score. Okay, and this could depend on where you jump it from. Okay, so this is for the pre-trade Macroprice state. All right, so this quantity needs to be estimated. Okay, this quantity needs to be estimated using artificial order simulations because our model does not feature informed and uninformed traders. Okay, it's purely mechanical and engineering oriented. Okay, so the second component is about order execution. Okay, we will assume, we will propose the following model. If we have a best bid limit order, okay, and its relative queue positions Q, it will be executed either at a random time alpha when the best bid jumps down, of course, this is a very conservative estimate because when the best bid jumps down, okay, the whole queue on this is depleted. Of course, your order is filled. Okay, but this is a bit conservative or pessimistic. Okay, your order might have again queue positions throughout time, and your order might be filled much earlier than this random time alpha. So it could also occur that with this relative queue position Q, the order will be filled at a random time beta when the macroprice Sn hits through a hypothetical exponential boundary. Okay, so this is modeling, and this beta is defined as the hitting time of the macroprice through this exponential boundary. In this model, we have a parameter B, okay, which depends on the relative queue position of the order. Okay, so let me use a picture to sort of illustrate. Okay, so in this case, we have these blue curves corresponding to the macroprice, okay, and this red curve corresponding to this exponential view boundary. And when this macroprice drops below this exponential view boundary, then we will assume the order is filled. Similarly, for this picture, okay, we are plotting alpha, meaning that the macroprice moves, and at this particular point of time, the best bidder moves down, the whole queue is completely depleted, then the order is also filled. Okay, so what is the time to fill for a limit order in our model is basically the minimum of these two random times. Okay, so again, we also have tried a few different models. Okay, we started with sort of a linear curve, but it does not work very well. So we have settled with this particular exponential boundary model. As I mentioned, the exponential field boundary model is trying to capture the fact that you don't have to be so pessimistic so that you wait the whole queue to be depleted for the order to be filled. Okay, then with these two key model components, okay, we can sort of write down what is the order score in our setting. So we have a condition on what is the current bid-ask queue imbalance. Okay, it's equivalent to condition on the macroprice. So if you normalize the best bid to 0 and the best ask to 1 tick, then the macroprice is just the bid-ask queue imbalance. Okay, so condition on these two microstructure features, we are computing the order score as the expectation of the time at the time of fill. What is the macroprice? And multiply by this indicator function. Okay, so here, as I mentioned, I have normalized the best bid to 0. Okay, so because we have the Markov chain model for the macroprice, and we have defined these alpha and beta through sort of hitting times of the Markov chain, one can easily compute this quantity order score using a first step analysis of the Markov chain, and you can very efficiently compute it by solving a discretized integral equation. All right, so I'm not going to give you the formulas, okay, but this is very easy to do. And next, I'm going to move on to talk about empirics. Okay, so in our model, we have three set of parameters. The first one, of course, is the transition matrix of the macroprice dynamics. And this is very easy to do. We just use the transitions of frequency of transitions. And the second component is that we need to capture the adverse selection cost. And what we are going to do is using artificial order simulations that I have talked about earlier. So we will estimate the adverse selection cost, mu, by the sample average of scores of those artificial orders, which are filled, followed by an adverse price movement. And the third sort of set of parameters is this PQ in the hitting boundary model, and it depends on relative queue position Q. Okay, so for each relative queue position Q, we try to find this parameter PQ by solving an optimization problem. So what you can do is you try to minimize the squared deviations between the model-produced order score with the sort of the sample average from the artificial order simulation. All right, so this is sort of the empirical result when we sort of try to backtest our model, and I'm only going to illustrate it using this one particular large-scale acceptance type. But we have done for 5 of them, and the picture basically have similar patterns. So it's probably difficult to read these texts, but we have 9 pictures, Okay, the top one, left corner one, corresponds to the relative position being 10%, meaning your order ranks at the top 10%, okay, in the bit queue. And for this one, corresponds to Q being 90%. Okay, so you are almost at the bottom of the queue. So what one can observe is that in each picture we have two curves. The blue one corresponds to the model, the empirical results. This is essentially the curve you have seen earlier in the picture in artificial order simulations. While the red one is from our model. Okay, so in general you can observe that these two curves match relatively well. So we also obtain a similar type of phenomena for other type of assets. But for example, this is for Bank of America, which is matching each other with really well. Okay. So what I'm going to discuss next is about deviation problems. Okay, how we can use our model in particular. Okay, so I'm going to be interested in this deviation problem on informed order cancellations. So market participants, especially the credit providers, they need a cancel signal that guides real-time deviation for canceling order or letting it rest in the order book. For example, it could help them to avoid getting adverse field and incurring a loss. Okay. So one approach that has been proposed in the literature is to formulate an optimal control problem or optimal stopping problem. Okay. In our work, we are going to use a completely different approach. Okay. We are going to rely on our order score model, then adopt an approach that combines the order cancellation deviation with learning. Okay, so in particular, we are going to consider the threshold-based strategy based on our order score model. We will cancel a limit order at best bit if the estimated order score from our model drops below a certain threshold. The question is, of course, what is the best threshold value? Okay, we don't know that before we trade, so we need to learn it while we trade. Okay, of course, when I say we trade, it means simulated trade. Okay, so how we can address this type of problem? One framework that can be useful is to formulate this problem of learning the best threshold value using a multi-armed value problem. Okay, so let me quickly go over what is a multi-armed bandit and its algorithms. So the multi-armed bandit problem is a very classical reinforcement problem where imagine you have a gambler who is facing a slot machine with 8 arms. Okay, and each arm is associated with uncertain different rewards. Okay, so you only can gain information by pulling these arms. Okay, you don't know what are these rewards. The goal of the gambler is to try to collect as much money or as much reward as possible by pulling these arms over many turns. Okay, so there have been many bandit algorithms proposed in the literature depending on the context and assumption on the reward process, but the general key idea of bandit algorithms is to balance exploration and exploitation. And in the bandit setup, we try to favor the most promising option, but with some sensible amount of exploration. Okay, so I mentioned there are many algorithms ranging from very simple heuristic ones like epsilon grading, which means that with 1 minus epsilon probability, you are going to chase the past winner. You are going to select arm which returns you the best sample average reward so far, and with epsilon probability, you are going to randomly choose an action, okay, to explore other possibilities. And the other ones that has been popular, including UCB, gradient variant, Thompson sampling, etc. So I'm only going to give you a sort of description about UCB. So there's no innovation here. Okay, all these things are known. So I want to focus on UCB because we have implemented many of these algorithms, and we find that UCB performs the best in our setting. So it's worthwhile to introduce UCB. So the idea of UCB is also very simple. Suppose you have k different options or k arms. What you do is you first play each of them one by one, and after k rounds, okay, then you start do this. Okay, so QTA stands for which arm gives you the best sample average reward. So this is sort of the sample average of a particular arm. And you just don't want to change the past winner. You also want to do some kind of exploration. So you add another term which is similar like a confidence bound. Okay. So for this term, it is inversely proportional to NT, which corresponds to the number of times this particular option has been selected. So if you have not selected this option or arm for many times, just for a few times, then you are going to encourage exploration. Okay? And we also have a parameter there, C, which controls the degree of exploration. All right, so of course the performance of these banded algorithms depend on the parameters. Okay, for example, epsilon gradient depends on epsilon, UCB depends on C. Okay, so let me illustrate the performance of the UCB algorithms with different parameters. But before I do that, let me put things into the context. Okay, so in table 3, I'm considering the empirical performance of a naive strategy where we do not apply any threshold-based cancellation strategy. We just put a limit order at the best bid, waiting to be filled. And if the best ask moves up, we are going to cancel the order. And in this case, I call it passive cancel. Okay? So of course, you are very naive, you just wait there. There's 28% chance that you are going to be adequately filled, meaning that after your order is executed, the price moves down. Okay? And a normal field situation corresponds to the case that after your order is filled, there are still people lying behind you. Okay, so that the Macroprice do not drop below the current best bid. And in this case, one can see that the score per order, which are simply called profit, but this is theoretical profit. Okay, this corresponds to our order score. The score per order is negative, and the score per trade is also very negative. Now, after you apply a banded algorithm, similar, for example, in this case, is the upper confidence bound. Okay, we have different rows. The larger the C, the more exploration you are going to encourage. Okay, so in general, what one can observe first is that the profit per order and profit per trade is much better than this naive benchmark. Okay. And second, you can see that the percentage of adequate field, of course, similar for the normal field, has been reduced almost by half. Okay? And in this case, because we have applied the threshold-based cancellation strategy, active cancel amounts for around 50%. Okay? So lots of orders are canceled, and if you combine passive cancel corresponding to the price move away and our active cancel, roughly speaking, you have 70 to even 85% of order cancellations, which is sort of consistent with what we observe in the hyperprecise trading setup. All right. So of course, as I mentioned, okay, the performance of these banded algorithms depend on the parameters. So in this case, for example, for theta rounds, let's see, 5, you have the best profit per order. Okay. So similarly, you can we can report all the other things, but in general. Let me skip this, and what one can observe, the only method I want to convey in this picture is that the profit per order and profit per trade are both positive. Okay, so even you apply very simple heuristics like epsilon greedy, you are going to be much, much better compared with the naive strategy. Okay, but in general, the profit per order is slightly worse than UCB. All right, so of course, a question that one might ask is that, can learning be really useful? Can learning really be useful? For example, we are applying these banded strategies over, let's see, the second quarter of Intel. And what one can do is that you can apply the threshold-based cancellation strategy, but why not just follow the previous best choice? Meaning that you have already have the data for the first quarter. Okay, why not just choose the best one that has been observed in the past? Okay. So I think the short answer is that learning can be useful, especially in the setting that when the best arm or best threshold may change significantly between this quarter to the second quarter, or even monthly. Okay, so let me take to the extreme and using this particular example to illustrate. In this example, I'm considering Bank of America. Okay, we can compute what is the profit per order under the arm with the best performance. So here one arm corresponds to one threshold. Okay, and for if you fix best arm, in this case, the profit you get is around 0.4 basis points. But if you apply UCB, in general, you can do better if you select these parameters appropriately. Okay, so the main message I want to convey you in this table is that learning can be useful, okay, in this particular setup. All right, so I think I'll quickly summarize. So in this work, we developed a stochastic model for storing a limit order at vector code for elastic assets. And our model takes into the Q position of order, the bid-asking imbalance, the price dynamics, as well as the adverse selection. So the main novelty in terms of modeling is to capture this bid-asking imbalance, okay, and propose a particular model to do order score performance measurement. And we have done empirical calibration and validation, and the results show that the model could perform well. And finally, we use our model in a particular decision problem in algo trading. Even though I have restricted our attention to order cancellation decisions, I believe it can be used in other settings, including choice of limit or market orders, etc. But our order score model is combined in our, in this work with a blended learning approach to develop engineering solutions in informed order cancellation decisions. And what we have found that is UCB appears to perform the best, and learning can be useful. Okay, so I think I will stop here and take any questions you might have. Thank you very much for your attention.
Thank you very much. Any question?
Yeah, I have one question. So, exploration is really an issue in your banded application. So, suppose say I just estimate using your simulator to estimate the expectation, and they pick up the largest one, rather than so randomize a little bit using say UCB or some other say ipso greedy methods. So can we generate still better results than say naive passive cancellation?
Yeah. So of course, so this is a picture that speaks to your question. As I mentioned, for this particular case, okay, we are looking at the first quarter of Bank of America. Okay, you have this model free, these curves. Okay, you can try to select a best threshold. Okay, select a best threshold, just a fixed one, okay, without doing any exploration or learning, just using a fixed threshold. And you find the best threshold, and the profit per order in that case will be 0.4 basis points. Okay. Okay, I'm running out of time, so. All right. So, but if you in the second quarter, okay, so you are doing, if you do UCB in this case, okay, what we find is that, for example, the profit per order in these cases can be better than this one. And this is already cheating a little bit in the sense that I'm kind of doing this profit per order for the best arm ex post, meaning that I'm already using the second quarter of data. If you use the first quarter of the first quarter of data, let's say if you use just the 2015 last quarter, okay, and then you select the best arm, it's going to be worse, okay, than this case. So in general, what we can observe is that if you just do fix the threshold, okay, it can be worse than a learning algorithm. Yes.
So this might be hard to do, but have you tried to compare the results of your method with the Lonely and Gunn or with the Allen and Jude?
No, we have not done any comparison in terms. Okay, so we haven't done any comparison with them. Okay, the reason, okay, of course there are many reasons, but one of them is that there are many reasons. Okay, so first of all, okay, we are doing such, we are proposing this performance measure using order score, which I don't think anyone has done that. Okay, they are doing completely different ways. Yeah. So the performance you look at is first of all different. Okay, the performance you look at is slightly different. Similarly, as I mentioned, even if you consider optimal control problem, okay, we are looking at like profit per order, profit per trade. I don't think they are doing that. Okay, I don't think they are doing that. They measure profit not with respect to Macroprice. Okay, they with respect to different benchmarks. So it is difficult to directly, doing some comparison. Actually, one of the motivation doing this kind of vendor learning is because in high frequency setting, okay, if you have optimal control problem, especially with multiple macro features or many variables, the optimal control approach is probably relatively more difficult to implement in an online setting. And this is why we sort of go to this learning procedure.
Yeah, in fact, optimal is not even true for these two papers because they present some sort of heuristics. They don't find the optimal solution.
Yeah.
That's why I was asking.
Okay.
About that.
Yeah, thank you for your suggestions.
Maybe as a follow-up to this question, so you propose this particular score. So if you write some simple stochastic control problem, is there an example where something like this actually comes out as the optimal rule, or is this just, so can you somehow micro-found this with some stochastic control problem?
That's certainly a very good question. So if we can sort of rationalize the threshold-based strategy would be optimal in a stochastic control framework, that would be fantastic. Okay, but
it's not where you
no, this is not. So we are sort of like, we propose like a credit score, order score, and then we just use it for division problem. We have not rationalized into a control framework. But yeah, that's definitely a direction to look at.
Shall we
Sure.
move on to the next page?
Thank you very much.
Thank you very much again.